Hello everyone, today is day 35 of Coding Every Day. Today is a Wednesday, February 19th, 2025 at 12:07 p.m. So I'm completing this Leetcode roadmap and I'm in the graph section right now. So today we're going to take a look at course schedule 2. I only have about 40 minutes today, so I don't know if I'll be able to finish in time, but let's just see where we get. Okay, so we're given prerequisites, where prerequisites of I is AB, that you need to take course B before you take course A. Okay, and they're labeled from 0 to num courses -1. And then, okay, so we have to return a valid ordering of courses to finish all courses. Return any of them. Okay, so course schedule 1 is you just return true or false if you can finish them or not. So now we have to return if we can finish them. Give an example. So the first step would probably be to make sure that you can finish them. So that would, I did this a couple days ago. I did do this a couple days ago, but so how you do that is you just check if there's a loop in the graph. So for instance, if these are your classes, this is possible because you can take A and then B and then C. If it's like this, then it's not possible to complete the courses because you can't start anywhere. Or even if it's like this, it's still not possible. Or like this, you could start with D, but you can't do B yet because A, and you can't do A because of C. So basically, whenever there's a cycle in the graph, we know that it's invalid. So I did it with, I just had a set called visited, and I would just copy it for every node. So I would just do a DFS, but make visited dependent on what node you're at. So if you had like A, B, C, so let's say it was like this. So at this point you visited A, here you're at AB, here you're at ABC, and then let's say we have F here. Okay, so when you go here, so basically this set means if you visit any of these again, there's a cycle. And then let's say our DFS goes here, so A, B, C, D, and then A, B, C, E. So we're good, but we still haven't, sorry, A, B, C, D, E. So we still haven't explored the whole thing. So then we're going to backtrack to this E, or sorry, this C, and we need to reset our visited set back to ABC, because if we encounter like D again, that's fine. There's still no cycle. But if we encounter ABC, that's not fine, because this would mean there's a cycle. This means there's not a cycle. So we have to reset this visited set. So then A, B, C, F, and then once this we see C, then okay, we know that there's a cycle. So the solution used recursion, and basically what I did is for every element in the stack, I added a copy of a visited set. But the solution did it so there was only one visited set, and you can just use backtracking. So I could try doing that. Okay, so DFS. So it needs, okay, so I think there was like a global visited. So this will take in a node, which is, I'll just say node. Well, first we have to build a graph. Okay, so I'm going to build a graph. Prerequisites is a list of int. let me just print pre. So it's this, right? Yeah, list of int. So for prereq in prerequisites, just to make sure. Okay. So prereq is a list that contains 2 integers. So I'll just say AB equals prereq of 0 and like that. So A is the course and B is the prerequisite. So if A not in graph, then graph of A equals empty set, and graph of A dot append B like this. So this should build the graph. So let's print it, see what this looks like. Okay, so here we have 1 is dependent on 0. I also want to say if B not in graph, graph of B equals empty list. Because I also want to note, yeah, 0 has no prerequisites. I also want to note that. So if we look at the other case here, 0 is dependent on 1, 1 is dependent on 2, and 2 is dependent on 0. Okay, so this would be like a classic cycle example. Okay, so this builds the graph. And when I say graph, this is just an adjacency list, basically. Just keep it like that. Okay, so now what we want to do, and do we start from any node? I think what we want to do is get every, so get all starting points. So a starting point is anything in the graph that has no prerequisites. So for I guess course is better. For course in graph, if not graph course. So if it has no prerequisites, then for now I'll just say starting courses dot append course. Okay, let me make sure that works. So print starting courses and graph. Starting courses is not defined. Whoops. Okay, so here it says 0 is a starting course because it has no prerequisites. Perfect. And here it says there are no starting courses because we cannot start anywhere. So in this case, obviously, it's false. Okay, so now what we want to do is call DFS for every starting course. And I think this is how we want to do it. And then I guess we just want visited to be reset to empty set every time. Okay, so let's make our DFS, which takes in a node. And then we can use graph. Should it take in visited as well? I think maybe it should take in visited. Okay, so all right. So stack equals node. Visited. Okay, so normally iteratively I say like this, and then I say while stack, but instead I think what I should say is DFS stack.pop. So I've never actually done DFS recursively here, so let's also pass stack. Okay, so if not stack, then I think we return. So let me just print, just so I get a feel for what's going on. This is probably not what we want. So basically we're just going to pop from the stack every single time. We also have to add, so like this maybe. So the node, the stack, and an empty set. This will probably change. Stack dot pop. Oh. Okay. So node equals 0. And then stack is, then it gets called with 0 again because 0 is in the stack. Maybe 0 should not be in the stack when we start. It should be empty stack. So if we try that, we return 0. Well, maybe actually, I don't think we need it for the first one. Well, we want to do our calculations down here. So maybe we should pass it. Start. Okay, so that looks fine. Okay, so now we say for neighbor in graph of node, neighbor dot append, stack dot append neighbor. Like this? Or do we just DFS? Maybe we don't even need stack. Maybe the whole point is that we're doing recursion. So would I just say here DFS neighbor? And then the base case would be if, well, eventually it'll just run out of neighbors, right? Well, you must say visited dot add neighbor. Then if okay, so here we would say if neighbor not in visited, then we will probably add it first. So we add the neighbor to visited. Like this maybe? I think a stack we don't need because we're doing it recursively. Okay, so we don't do that. We don't do this. Okay, so for every node, we're going to just DFS its neighbor, and then let me just print neighbor. I know I just deleted this, but node. All right, let me see if that gives me an infinite loop. It didn't. Node equals 0 here. We have nothing. Oh, because it has no starting courses. Yeah. Okay. Let me set. Let me just define a graph real quick. So let's say that 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. Okay, let's see if this outputs 1, 2, 3, 4. Okay, it did not. Well, we need something that's dependent on nothing. So let's say 0 is dependent on nothing. No, let's say, okay, so 4 should be dependent on nothing. 4 is dependent on nothing, like that. So 4 is dependent on nothing, 3 is dependent on 4, 2 is dependent on 3, and 1 is dependent on 2. Okay, so we're only printing 4 here. So let's see if this works. Neighbor, doing all right on time. Wrong indentation. Okay. So is this part? Yeah, so it has no neighbors. Okay, so right now we're saying saying 1 is pointing to 2, 2 is pointing to 3, and 3 is pointing to 4, and we're starting at 4. So we should really point them the other direction then. So should we do it like this? But how do we know? This way is easy because you know that you could start with 4. So do we need a two-way graph? Like, I don't remember how I did on the other one. So we probably want to start with this one and then go like this, because this would give us our path for the problem anyway. But to get our starting points, we'd have to, I mean, okay, so let's say graph of b dot append a, like this. And let's see. Okay, so now it's thinking that 1 is a starting point. So I have to revamp the starting point thing. So I think what we'll say is starting courses is a set. With every, so it'll be from I don't know if you can do set comprehension. So 0, well, I for I in range 0 to the number of courses, right? Length of graph. So let me just print this. So this will give us, I just want to see if length of graph. So length of graph, if it actually equals the nodes, it should, because every node. Yeah, okay. So I want this to be a set. A set, and then what we'll do is we'll say for course in graph. I was thinking we could just look at every. It might just be better to have two dictionaries. So one that points this way, so you can find the starting position in O of n, and then one that points this way, so you can like traverse. So maybe we could call this so like a that's a bad name. So what there's called prereq, and I guess I'll say course. So in this case, if we do A to B, it's that would be course to prereq, and then we'll have prereq to course. And so here we'll say prereq to course of B dot append A. And then here we'll say course to prereq of A dot append B. And then in both of these, if A not in graph, A not in B not in. I'm guessing there's a better way to do it, but this makes sense to me for now. I mean, alternatively, I could just have it be only this way and then see whichever node is not in one of the neighbors, but for that it would be like V plus E, so this way is just linear. Okay, so course to prereq, whoops, alright, course to prereq. Of B equals empty list, of course this one is empty list, A equals empty list. Okay, so now I want to print those two. So print course to prereq, and then I'll print prereq to course. All right. Okay. Got about 15 minutes left before I have to go. Okay, so all right, so course to prereq. Yes, this is right. So the course 0 has no prereqs, and then this one is 0, so prereq to course. Okay, that's perfect. So now starting courses, we'll just do what we did before. So starting courses equals I guess we could say course in graph. Course for course in graph if not graph course, like this. Then I'll just do this. Okay. So starting courses is not being outputs. It seems. Am I returning? I'm returning. And then here we want course to prereq. Okay, 0, and then this one should be empty. Okay, perfect. So we get the starting courses. Okay. And then we're going to use... Okay, so then we'll pass the starting courses, but for neighbor in prereq to course, like that. Okay. Graph. What? Okay. I don't think I use graph anywhere else. Okay, so we start at 0, neighbor is 1, and then we go to 1. Perfect. Perfect, perfect, perfect. Okay. Let's clean up a bit. Get rid of that. Get rid of that. Actually, we'll keep that. That's fine. We can get rid of this. Honestly, I'm also just going to do imports from collections, import default dict like this, and then I'll just make these collections dot default dict of list type, and then I think I can comment all that out and it's fine now. Alright, I'm just gonna leave it. Doesn't matter. I'm trying to optimize too early. I always do that. Okay, so this should. Alright, this is back to what we had. Okay, so I want to keep track of. So now I'm trying to do the visited thing with the backtracking. So we'll pass, we should pass a set with start in it. I want a bigger graph. So, okay, let's do prereq to course. But now I have to change the other one too for this to work. Say DFS one. Okay. Is that where I want to start? Yeah, that's where I want to start. Okay. So starting courses is 0. Let's just ignore that. Okay, so 1, 1, neighbor is 2. So we visited 2, we visited 3, we visited 4. Okay, so now if I give, let's say I give 2 an additional neighbor called 5, and 5 also has no prerequisites. So the way that this should work, it should do... Yes. Okay, so here, I also want to specify node like this. So it goes 1, 2, 2, 3, 3, 4, and then 4 is empty, so it'll backtrack to 2, 5. So I want this list to undo every single. So I think after here we would say visited dot remove neighbor like this. Okay, perfect. Perfect. Okay, so yeah, when we're at this, if we visit any of these, we're dead, and then here, if we visit any of these, we're dead. Okay, so we want okay, so if it is invisited, so else, or we want to exit the program. We want to, so here there's a cycle, so we'll just say cycle detected. All right. So let's get rid of this test case and let's put this back in. And let's run it. So this, so if there's not a cycle, I should also probably remember the path. Yeah. So I could just have a variable called path, which I will make an empty. We'll start at start Well, path actually has to be for each DFS. All right, let's just make it for one so we at least get past the test cases. So path will be, we'll start at start. And then if it's not invisited, basically every single time I want to add path. So path dot append node. Okay, and then I guess at the end for now, I'll just return path. So path is a we'll say path equals empty list, and then we'll just okay. Yeah, so we'll just do that. So my output was 0, 0, 1. So maybe path should be empty list because we added anyway when we start. Okay. I'm expected to go to 2 here. I did not know there was a 2 here. Oh. Okay, so we need, so num courses is probably important. Yeah, I wish I read that earlier. So there can exist a course, I guess. At the end, if it's not in anything, then we can just make it empty. So like, for I in range num courses, if I not in course to prereq, so if it's not a course at all, so it hasn't appeared in either one of these, we only need it in terms of the starting condition, right? We can start path. So I think it's fine. And I think what we can say is we'll say here path equals this. And then if it's not there, we can just start the path with I. And then here we don't need that. So my idea is, so we'll probably do 2, 0, 1 is what I'm thinking will happen. Yeah. Okay, so this will be wrong. Okay, so so when a cycle is detected, we would like to return false. Okay, so what's the best way to do this? So path, I think path is actually fine how it is right now. I'm just going to make it list comprehension because I optimized too early, I guess. I for I in range num courses. If I not in courses, sorry, course to prereq, like so. Let me just make sure that works again. Oh wow, we got through a lot of test cases with that. So I guess the first test case is, right now our code doesn't handle cycles at all. So, okay, so first of all, if not starting courses, so if there is nowhere to start, then we want to return empty list is what it said as the null condition. Yeah, okay. So basically if there's nowhere to start, then we'll return empty list. Okay, so So for cycle detected, I guess what we could say is cycle equals true, and then here just say if cycle return or we could have this return true or false, I guess. So here, let's say false, there is no cycle, and here we'll just return true. And I could reverse the logic here, but it's fine. Okay, and if we get to the end, okay, so cycle equals this. If cycle, return empty list. Okay, this. So there is no prerequisites, so if length of prereq to courses length of prereq to courses equals 0, return 0. I'm not confident in this. Still not confident in this. Okay, that's not why. Okay, prereq to course. Like that. Okay, so there's nowhere to start, so it's returning that. So maybe I should do this one first. And then maybe just instead return I for I in range. Okay, so here, prerequisites. So 1 is dependent on 0, which is dependent on, it's also dependent on 2, and 0 is dependent on 1. Okay, all right, I have to go. I'll be back. But so this one is a cycle, but it's not detecting it, so I could figure that out. But I'll be back. Hey everyone, I'm back. It's been like an hour and a half-ish, so if I remember correctly, I couldn't, sorry, this must be funny if you just are watching the video, it was a second ago. I was doing something with cycles, and this should have been a cycle, but it's not. Okay, so let's look. So okay, so here 1 is in visited. So I returned true. So maybe I just have to stop everything from executing. So if cycle, just keep returning. Probably should have submitted there. Cycle does not exist. All right, let me do it like this. So let's see when the cycle gets detected here. So cycle is detected right here, and then this returns true. And then let me see, for print, let's say outside cycle and cycle. So let's see what's, let me add this as a test case here. So let's see what this prints. Outside cycle false. Okay, so somehow we're returning true here. Okay, so we're returning true for... Okay, so we're returning true for this call. And then for another node, we're returning false. Yeah, okay. So I don't know if there's a better way to do this. So first, let's say if neighbor invisited, then we will print cycle detected and return true. And then if we're here, okay, so this should change nothing. We should still be, yes, okay. So this is returning true, and then let me print, this will illuminate what is happening. So if I print returning false here, this should happen after cycle is detected. Yes, okay. So it's still exploring. So we basically just want a Boolean. So I could just say this. So if cycle found, then just get out. So return return true. And then here we'll say cycle found equals true. And here we'll say cycle found equals false, like this. So it's still calling it. If not cycle found, maybe. Oh, wait. Okay, if cycle found, then return empty list. We don't actually want to call DFS again. All right, what's happening now? Same thing. Maybe it's because I'm returning false. I don't know if I should return false. All right, so let's think about how we want to structure this here. So all right, so what's our base case? So we could do every DFS has to return true or false, because here I'm not returning anything, right? So okay, so or I could make a global variable called cycle found, and then when we find a cycle, we'll basically stop everything. So we're finding the cycle correctly here, and that's good. And then the other ones, no cycle found, right? So that's good. So what if we just, okay, let's try the global variable approach. So we won't return anything, we'll just set a variable. Okay, so here we have a variable called cycle found. So let me print this out. Cycle found. Whoops. Okay. Cycle. All right, cycle found. Don't want this. Okay, so when we find a cycle, we'll make it true. So So we shouldn't return anything, and cycle found equals false. And we only... I'm going to get rid of this for now. Okay, so let's see what this looks like here. Okay, so cycle found false, cycle found false, cycle found false, cycle detected. So it returns. So, and then cycle found. So this is what I'm a little confused about. So when it finds the cycle, I guess these two calls, okay, so these two calls when neighbor, because we're in a for loop, maybe, is that what's happening? So if we said if cycle found, then return, would that fix it? Nope. What if I put it here also? It's indentation error. I mean, I don't think this code is reachable. So let me print, is it outside cycle perhaps? No. Okay. So let me print entering DFS with start. Maybe it is this for loop. It only enters once. Okay, so why is it return? Okay. All right, so this is not working. So the other approach, I guess, would be each DFS returns a cycle. So we get to the end of the DFS. What is the base case for the DFS? I don't really know. I guess it'll just end. So I could say cycle equals false. Then here we could say cycle equals true. And at the end we can just return cycle. Okay, let's look at this. So this returns true. And then it would go to the next neighbor, which then can go to this and then exit out and go here. Okay, so the problem is that we're finding it within this for loop. So I don't understand why, if we put if cycle, why this doesn't work. Oh, because cycle is local? But the other one was not local. Well, the whole for loop should not execute. Right? The for loop I don't think is executing. Because we call this, it returns. So the for loop is not being executed at all. Because we're returning for the whole function. but there's still stuff in our recursive stack. So this will get called again for these, like the other ones. So returning false. Do I need a return there? Okay. So that seems to be working. Okay, so the other one worked. Okay, let me understand what's going on. Okay, let's just look at it. Okay, so we enter DFS once. Okay, so cycle is false. Return cycle. All right. Okay, so we start with cycle equals false. Node equals 2 and visited equals 2, and then for every neighbor, so there's just one neighbor, and that's 1. So neighbor is not in visited, so we add it, and then we call DFS and then return this one. So this function will just return, okay, so we don't want this part down here. Or do we? Or do we say cycle equals this? So we want to return the answer of this, which will keep returning the answer of this. Okay, so right now this value is either true or false. This cycle thing is strange. I don't think this makes sense. Okay, so if we get rid of that. So is this false? So if we go through every neighbor and we return its DFS, well, we would need some sort of base case. Return false. Okay. So this starts to make more sense. So if there's a cycle, we'll return true, which then for every everything else would also be true. This code is unreachable. Right? Because this code is unreachable. Because this function will either return true if there's a cycle, or will return... So when do we return false? I think we need like an if something. Like if we need a base case. Because this code is unreachable, no? So we're returning true. Here we are returning none. So I don't know where to return false. I think I understand what's going on. So, okay. So let's imagine we have a graph. 1, 2, 3, 4. Okay, so we DFS node 1. Okay, so we say DFS of 1, and that will return DFS of 2. And DFS of 2 will return DFS of 3. And DFS of 3 will return DFS of 4. So maybe we could say if you have no neighbors, then you return false. But what about this? Okay, so DFS of 3 in this case will just equal DFS of whatever neighbor. So I think we need to take all of them, and if any of them are true, then we should return true. So if we have neighbors have cycle, and then we make it a list, then here we would say neighbors have cycle dot append. So it's going to store it. So we would say DFS of 3 equals a list. So it would be DFS of 5 and DFS of 4, like this. And then if any of them are true, then we'll return true. Otherwise, we return false. And our base case kind of, so if obviously we need to calculate what this is. So if we look at DFS of 5, that would be an empty list. So this should return false. So if it has no neighbors, that should return false. There is no cycle. Okay, so I'm going to do a bit of testing here. Okay, so let's imagine I have a list of Boolean values. So true, true, false. And I want to say any of a list and print answer. So that's true. If they're all false, then it's false. Okay, what if it's an empty list? Is it false or true? False. Okay, so we want to use the any function. Okay, so, all right, so we're going to check that. And then for this node, we want to return any of neighbors have cycle, like that. My mistake. Okay, let's see if this is easier to follow. Neighbors have cycle is not defined. Neighbors have cycle. Okay, typo. Okay, so let's look at this here. So the return value is true. which is what we want. So this looks good. I think this is good. I don't know if there's a better way to do that. Maybe instead of any, we can make this a Boolean and set it to false. And then we can set neighbors have cycle to that DFS only. Yeah, okay. So we're going to say if DFS of neighbor visited path, so if it returns true, then neighbors have cycle equals true, like this. And then we can return neighbors have cycle like this. So it's doing the same thing. So we still want to explore every neighbor, and if any of them, we never set it to false other than here. So I think that's doing the same thing effectively. Neighbors have cycle is not defined. Another typo. Okay, it's in oh, it's because I have cycle. There we go. So these two are both spelled incorrectly. Okay, so the output here is false. This is edge case, and this is true. Okay, so now this will. So now I think we do the same thing here. So for each starting course, we want to do that. Well, until okay, so cycle exists in the graph is false, and then if DFS start path, then we say cycle exists. Well, I guess here we could just, we're in the outer function now, right? So we can return empty list. And if we make it to the end, so we don't actually need this variable. Okay, so if any of them have a cycle, then we return empty list. Otherwise, when we get to the end, we return path. Okay, great. So it just took some thinking. Yeah, so my mistake, if that was really obvious to you guys watching. A problem that I'm trying to, so I'm happy about this because this was, I did a DFS recursively, and I didn't know how to do that, so I kind of just figured it out. And I also did backtracking elements here with adding and removing. And yes, okay, so there's a lot to like here. There's a lot to like for sure. This is kind of ugly. Let's say C4C. Okay. This is also ugly. But whatever. Okay, definitely a lot to like here. Was able to figure this out. Okay, yeah, so thinking recursively, I should more rigidly kind of define what my function is returning. I feel like I did great with the add and remove from visited. The path was a sort of a good idea for that. The two graphs, I don't know if that's necessary. I don't know if this solution is overly complicated. It probably is. But I don't think it's really that inefficient. We basically DFS times the amount of uncontested courses there are. So it's probably just in one DFS right yet. I'm not sure if I even have to do this. Well, yeah, I definitely do have to do this because let's say there's a disconnected graph. So if it's like 6, 5, and 3, 7, right? I need to start with every uncontested one, or else I can't determine if there's a cycle, because I could just do it for this one and that one's good, but if there's a cycle in this one, yeah. So my solution is basically V plus E times the number of nodes in the requirements. So which I think is fine, because if every node has no requirements, then like the depth first search doesn't exist anyway, so this will like approach 0. So as this approaches n, this approaches 0, so I think it's kind of fine. Yeah, so that's, I wonder if there's a better way to do this, but yeah, so it's been accepted. So thank you guys for watching and sticking with me. I know it's probably not the best way to do it here, but I think it's pretty solid, considering that was my first recursive implementation of a DFS. And I also did it a different way from the way I did Core Schedule 1. So that being said, thank you very much for watching, and I'll see you tomorrow for day 36.